So, hello and welcome back. And today will be another interesting evolutionary algorithm called as the particle swarm optimization. So, since we already have a good background of the working of any evolutionary algorithm for that nature, let us directly make a fitness landscape. So my fitness function is something x1 square, x2 square plus x1 minus zero point 0.8 the whole square plus something something something. I plot it around. Last time we were primarily using 1D graph with x-axis as x1 and the y-axis as a fitness value. This time I'll use a contour. So that's my x1 axis, that's my x2 axis. There is a global minima out over here. That's how the contours go, and there are some local minima around over here. And another local minima around over here, and let's say another local minima around over here. And I need to search for this global optima, and I need to escape these local optima. And therefore, obviously, I will be using evolutionary technique. So I take in random individuals like any evolutionary technique. I take in random individuals, and by taking in random individuals, I will be seeing that can I move them around so that they can eventually come to this global optima. So the individuals now will be called as the particles, and hence the particle swarm optimization. And a particle will be associated with a position which is shown over here. So that's the ith particle xi. Along with that, every particle will be associated with a velocity. So now imagine it like a swarm of robots, and the only way that I can move the robots is by giving in a velocity, and velocity is a vector. So the only way that I can move the particles is by controlling the velocity vector. It's suddenly a control problem. I need to give in velocities to all the particles, to all the robots, such that they start moving. So position is a two-dimensional vector, and velocity is also a vector. So what's the velocity in the x-axis or in the x1 axis, and what's the velocity in the x2 axis over here? So obviously I will have a very simple algorithm, and all that my algorithm will say is that I should be able to guess the velocity of the particle I at any time t. So that's what I will be calculating using some control techniques, using some intelligent techniques. And then I will say that the position of the particle at time t plus 1 is nothing but the position at time t plus the velocity vector. Now, why not a delta t? Delta t is a constant over here. So I say at every unit of time. So that's what's my equation. So my harder task is, of course, how do I make a control law? How do I control the speeds of my particles? How do I control how do the particles move? And the entire intelligence is around over here. Now, in order to move the particles, let me define a few strategies and let me define in a few techniques which will be entirely a guesswork. So I define a quantity which is called as the x best. It's defined as the best position with the lowest cost, highest fitness, or let's just say with the best fitness seen by any particle in its journey at any point of time. So the particles are moving with velocities, with speeds. I'm giving them some speeds. The particles are moving. All of them, they just look around and they can communicate to each other and they let each other know, you know what, in the position that I am, this is the fitness value. In the position that I am, that's a fitness value. And then you calculate the best fitness value, the lowest cost, and you say this is the best solution that we have found so far. This is the position which has the least cost. This is the position which has the highest fitness. So that's something which is inherently extremely good. So out of all these particles, I think this one is actually the global optima, but all the particles are pretty far off. And this is the local optima, but then the particles are extremely close. So currently it appears that this particle is the one which is currently X best, the best particle so far. And therefore I say that let me take in a greedy strategy. So I say strategy number one to move the particles is what's called as a greedy strategy, which says move all particles towards X best. So let's say that this is a swarm of robots and they are finding some gold, and here it is. So the further away I move from this gold, the glitter reduces. So it's a really bright gold and it can be seen from a distance, and all I see is the brightness value of it. If it's more bright, I'm closer. However, this would have been a very simple problem to search for gold. The problem is that there are three more jewels which are also bright, but I just want to search for gold, and that's exactly what happens. This particle says I'm at a very good place, I see bright light, and everybody says here is the gold, and they all try to go over here because the light is extremely bright. That's a greedy strategy, and the greedy strategy says that move every particle towards places where the best recording has been done. So let's write down what the strategy is. So the strategy is called as VI at time t by the best strategy, also called as the global best strategy, is equal to, so in which direction should there be a force? My force for any particle xi, say here, should be in this direction. So towards X best. So I say it is X best minus my current position. And let us say, so that's a direction, so it will be divided by the norm of this vector. But then I say that further away the particle, the higher will be the speed, and the nearer to be the particle, the smaller will be the speed. So this is what will become my direction of the motion. And then of course, I multiply it by a proportionality constant, which is C1. So this is my force which is acting on this individual. It's C1 times x press minus xi by my global best strategy. So imagine it like a potential field. This particle is actually trying to attract everybody towards itself with a force which is proportional to the distance. So these particles will have smaller force and these particles will have a larger force, and hence I say that that's the direction, that's the magnitude and direction of the force multiplied by a proportionality constant is my current speed as per the global best strategy. And let's try to do a very quick dirty simulation of it. So what really happens is this particle tries to go over here, and as soon as it goes over here it actually gets a better position. This particle doesn't move, and hence very quickly this becomes the global best. So this is the one that becomes the global best. And then this particle moves over here, this particle's no change, this particle moves, no change, this particle moves, no change, this particle moves over here. This will actually get close to this minima as well, but soon actually what will happen is that this one is extremely good, so they all move around over here. And in pursuit of which, what really happens is when this particle moves around in that area, when this particle moves around over here, it gets to this point, and this point may actually be better than this. This was the global optima, this was the local optima, and hence it starts attracting everybody towards it. So then maybe this particle was here, and suddenly the focus of attraction changed. Suddenly a person said, hooray, eureka, I found a better position. So now it starts attracting everybody. Maybe this particle was here by the time this moved here, and hence it tries to go around over here, but it finds an even better position. And now it says, hooray, I found an even better position. So you see that all the particles are moving towards the so-called global best, the best known so far. So this is what is called as the global best. So as all the particles move towards the global best, what happens is the global best keeps on updating itself, and because the global best keeps on updating itself, soon you see all the particles are actually pretty much near the global optima, and hence the strategy actually works. And because the strategy works, I am like, okay, that is really a good algorithm, that's really a cool algorithm, and because that is really a good and a cool algorithm, therefore mostly what will happen is that all the individuals will be able to get towards where they want to get towards, ideally good location, get towards the global optima in that case. But then there's a caveat, of course. There's a problem with that strategy, that most probably here we were lucky that there was one individual which on its way could get near to the global optima. In reality, the chances of this happening are extremely small, and if I only use this strategy, what is practically gonna happen is the fact that what's practically gonna happen is that my individuals will soon show a convergence towards a local optima instead of the global optima, and hence the strategy will lead to a convergence into local optima, most probably. So I'll do the same old trick. I will do the same old thing that we did last time. So in genetic algorithm, I said, can I please make individuals at reasonable places do something and just stay there for a while? Maybe they find out what are better places. Maybe they get towards something interesting. Can I just hold on the particles for a little time towards their own area so that they just do a little bit of an exploration there? And because they do a little bit of an exploration there, they end up in getting towards promising places. So I define another quantity. So let's say strategy 2. And this is called as the personal best strategy. So first let's define a term. So this is called as the personal best, or the best position seen by particle I in its journey so far. So that means every particle has a memory, it has a history of where all has it been, and the best place that it has personally, without talking to everybody, without communicating to everybody, the best place that it has personally seen, that is something stored explicitly separately. So this is the local best, and my strategy is, of course, so strategy 2 is the local best strategy. I, instead of trying to go towards the global best, I go towards the local best. And again, a proportionality constant C2. So let's look at it over here. So this particle moves, let's say it moves towards global best, it moves towards global best, it moves towards global best, or last time we took this particle as an example, so this time let me change in the particle and see what really happens if I take in a new particle. So this goes towards a global base, this goes towards a local base, but then there's a force which is saying that, okay, there might be a optima nearby, there might be an optima nearby, and therefore take some pains in order to go near towards your local this one. Don't just leave it, which I will do if I just follow this line towards my current global best. So there's another force that tries to force it towards this region, and this is the local best. So the best position that I have seen so far is actually, it goes a little bit up, so it's actually here. So there's a force constantly in this direction, and you're actually correct that if I go over here and I add just a random force, then I might actually attain a better position than this one. I might start attracting in a whole lot of people. So what I really did is that there was a force that I applied that constantly avoided the particles from moving towards the global best solution. It said you are changing modality, you are going towards some other modality, you're going towards some other place. So instead of going towards some other place, you just try to explore more in your own modality. And that is first come towards your personal best so far, then a random movement may happen and it may actually accidentally go somewhere where it attains a better position. So this is the personal best strategy. This is the local best strategy. So it tries to resist convergence towards this optima, convergence towards X best. It tries to say I'll stay at my own locality and try to explore that more. And using these two strategy is what we say that particles swarm optimization individuals move. Now there are two strategies. I need to select one of them. So either I could say strategy 1 is better, only use that, or strategy 2 is better, only use that. And it turns out that neither of them is better than the other. At some situation, global best will be better. In some situation, local best will be better. Global best is trying to get quick convergence. Convergence is good, but local best is trying to resist, is trying to do more explorative things, trying to say that I'm delaying the convergence so that the local areas can be explored and better are the chances of escaping better are the chances of escaping quick convergence to global optima. local optima, represented by x best so far. So I need to really fuse in the two strategies. Now, if I was one individual, I would have made a very intelligent guess in every situation which one is better, this one or that one, try to analyze it up and so on and so forth. But what really happens is that I have too many individuals, so I say that my VIT at any point of time will be W1 times the first strategy plus W2 times strategy 2. And because there are many individuals, for some I will have W1 higher and for some I'll have W2 higher, which means W1 is taken randomly for every particle and W2 is also taken randomly for every particle and for every axis. So it's random for all particles and for all axes. So my equation becomes VIT is equal to, strategy 1 was C1 times x best minus xi. Strategy 2 was C2 times xi best minus xi. They all suffixed t. And the weights are random, so plus R1 times and plus R2 times. So what happens for some individuals, for some particles, local best dominates, for some others, global best dominates. And it's this thing also adds stochasticity, this thing adds randomness, which is the essence of every evolutionary algorithm. So evolution is something which is completely random, and this also adds in randomness. Now there's another term that I will add, which is called as a momentum. So it's omega times VIT. So let's understand this strategy. In terms of strategy, it's simple. So in terms of strategy, all that this says is keep going in the current direction. So wherever you're moving, just keep on moving in the same direction. Wherever you're going, just keep on moving in the same direction. Now, essentially, it's also important to understand if there's something hidden in this strategy. And what is hidden in this strategy is exactly the same that is hidden in the momentum term of the backpropagation algorithm. It's exactly the same thing which is over there. So let's discuss this in a separate diagram. All the others were cluttered. And I just draw, let's say, x best, and I say that's the only strategy. And this is my xi. So the particle goes like this, like this, like this over here. Now what I can do is, here the velocity is in this axis in the same direction. So as long as my velocity in any axis is not changing sign, therefore I know that I'm traveling in the same direction in that axis, and therefore I can probably, instead of taking small steps, I can actually take larger steps over here. So that's xi and that's x best. I can start taking longer steps over here because my direction is not changing. So I know that my goal, my x best, the thing that I love is right over there. It's not changing direction, it's right ahead. So you walk fast. So if you look at this term closely, so this is the positive x-axis, or that's a positive x1 axis. And because that's a positive x1 axis, you're moving right. So at time 0, you moved right. That means VI0 was positive. Next, what did I do is VI1 is a positive term plus whatever comes out over there, which is also positive because it's on the right. So it's VI1 is equal to a positive term plus something. So I took one right. So let's do it again. I took one right. This is VI0. Then I had a fraction of this velocity positive plus another positive term. So this is VI1. Next it is a fraction of VI1 which is positive plus another positive term. So that's VI2. Next it is a fraction of this VI2 plus another positive term. So as long as I am confident that my goal is ahead, my x best is ahead, I am increasing my velocity in that axis. But then of course you will see that this has a problem. So momentum of course has a problem because the next step will be a fraction of this thing, which is here plus this thing will again be positive, so it will become over here. So that's VI4. And hence I overshoot the global best because of momentum, and that's bad. I overshoot because of momentum. But now let's not just say that momentum is bad. Let's not just say that momentum is bad. This is momentum. So let's not say that momentum is bad, and let's give it another chance. As of now, it was very good because it accelerated going towards x best, and suddenly it becomes bad because I overshoot x best. Now what happens is VI5 is a fraction of this thing, which is a positive term, plus this will become negative because now x best t, which is here, minus xit, which is here, is in this direction. So it's positive plus something which is negative. And because this is VI4 was extremely large, so therefore what happens is I go here and unfortunately I again overshoot, so it's still bad. But now what happens is that this term becomes positive. It's something on the right minus something on the left, so it's positive. So it's a fraction of this term which is negative plus a positive term. So now what is actually happening is, so that's VI6. So if you look at, now I'm changing directions. It's going positive, negative, positive, negative, positive, negative, positive, negative. Or if this is x best, all that I'm going is I'm oscillating over here. Now when oscillations happen, if this is positive, this is negative. If currently I need to go on the right, previously I went on the left. If previously I went on the right, now I need to go on the left. So it changes. So my step size reduces because it becomes positive plus something negative, or something negative plus positive. So whatever correction is there, this is reduced by this quantity, and therefore my step size actually reduces, and therefore now the step size will continue to decrease, and slowly I'll land up directly at x best. So the momentum is something which is absolutely interesting because when I am not changing sign, it's accelerated. When I am changing sign, it is decelerated. And that's exactly what you want. So you are driving a bike, when goal is far off, you go faster and faster and faster, you overshoot, then you start decelerating as you turn around and get back. So if you're changing sign, you decelerate and your step size is reduced so that you can perfectly land at x best. So that's what's the role of momentum. So finally, this is my final equation, and that's how the particle swarm optimization works. The only thing that you need to do additionally is apply limits. This speed could become extremely large, and that's dangerous. So you say the speed limited at, so this is the speed of the velocity of the ith particle at time t after applying the limits. And let's say at the axis, so there was a x1 and an x2, so at the axis j, so that's, I mean, VIT is a vector and VIJT is what becomes a scalar. So if it's more than Vmax, I will apply a limit of Vmax. So it will be always under Vmax. And then if it's less than minus Vmax, I'll also apply a lower limit. So basically, if my limit is 1, so I have a constraint that VIT limited always needs to be between minus 1 and 1. So if it's 1.8, I limit it to 1. If it's 0.8, I limit it to 0.8. If it's minus 0.8, I limit it to minus 0.8. And if it's minus 1.8, I limit it to minus 1. So it always stays between Vmax to minus Vmax.